right, let's start out with a summary of separation procedures and techniques in the lab. First is filtration. Filtration is the process that separates a solid from a liquid in a heterogeneous mixture. Filtration is the method of choice to remove solid impurities or components from a liquid. It can be performed by applying a vacuum as well to speed up the filtration. The process involves, as you can see in the image, pouring the mixture through a specially folded filtration paper supported by a funnel and letting gravity pull the liquid through the small pores in the paper, just like a coffee filter. So we would take our mixture, maybe it's like a compound that we precipitated, right? Think of a reaction of two ionic aqueous salts, and we mix them and we form a precipitate. And we want to know how much of that precipitate did we produce. So we have to separate it from the rest of the aqueous solution. So we would pour the precipitate and the aqueous solution into the funnel with the filter paper, and the spectator ions and the water would drip through the filter paper, leaving the precipitate behind, which we could dry and then get the mass to find how much of it we produced. Chromatography is a technique that we use to separate chemical mixtures into individual components. The mixture is first dissolved in a fluid called a mobile phase that is allowed to pass through a stationary phase. The various parts of the mixture travel at different speeds throughout the stationary phase, causing them to separate. There are 4 major separation processes that use the mechanics of ion exchange, surface absorption, partition, and size exclusion. Polarity of the solute and the solvent is also used for this separation technique, which can be both qualitative and quantitative. So let's look at a couple of examples here. Paper and column chromatography. So I'm going to start with the example of the paper chromatography on the right. And so what you do is there's this container with a lid here that has a little bit of solvent, okay? And where the top of the solvent is here, we would have put a small amount of our original sample, our original mixture, dissolved into that mobile phase. And what happens is the solvent starts to climb up the paper, and you can see our sample being separated out into these various dots. And quantitatively, we can measure how far up the paper do we get each of these colors separated out. Now, why does the red separate here, the purple here, and the blue here? Well, what happens is as the mobile phase is pulled up the stationary phase, which in this case is the paper, the colors that take longer to come out are more attracted to the solvent, whereas the red is more attracted to the paper, the stationary phase, or less attracted to the solvent. So there's this competition between the parts of the mixture, between the mobile phase and the stationary phase, and the colors come out as they are less attracted to the solvent and more attracted to the paper. Okay. Another type of chromatography is this color chromatography. And so we have our stationary phase here, which is this liquid, and we loaded our sample here, okay? And our sample is able to go through the column, and we can open the burette to allow the solvent or the stationary phase to drip as it goes through. And you can see that as that sample goes through the stationary phase, it begins to separate out again. And you can collect each color in a separate container as it separates out. And the principle by which it separates is the same over here. The weaker interactions will separate out first, right? Like we said here, the weaker interactions will separate out first. The stronger interactions will separate out later, okay? And which method you choose will just depend on what is in your mixture and what kind of interactions it is that are holding that mixture together. Distillation is the process of converting a liquid into a vapor and then subsequently reverting back to a liquid. We use this process to separate liquids from non-volatile solids or even a mixture of two liquids. This process capitalizes on the difference of the boiling points. So here's what we have. This flask has the mixture in it. Okay, we heat it and we get a vapor of that mixture, right? Or vapor, whatever is boiling first. Okay. So again, we're capitalizing on the difference in the boiling points. And so what happens is the parts in there that vaporize first will fall down this condenser tube. So this is cold. And what that will do is turn the vapor back into a liquid, and that liquid will drip into the receiving flask. So this is the distillate, okay? So this would have the first boiling point, the lowest boiling point, and what's remaining here would have a higher boiling point, okay? So you can connect the flask to a vacuum to support a lower boiling point to avoid decomposition of the mixture if necessary. So you don't want to overheat and then decompose your mixture. Gravimetric analysis is a process which determines the mass of a solid substance produced usually by mixing two liquids or aqueous solutions. Precipitation gravimetry uses a precipitation reaction to separate one of the products. The solid product will be filtered using quantitative filter paper, washed and then dried. The mass of the solid recovered will be used to calculate the percent yield using the stoichiometry of the reaction. So this is another filtration technique, right? We've talked about filtration already in this notebook, but we can use gravimetric analysis as a part of our filtration. The recovered solid product, which will be on this rinsed and dried filter paper, can be ignited along with the filter paper to convert to a stable oxide or sulfate to make a quantitative analysis. The special filter paper will burn off without any residues. So this is why you want to use an actual filter paper and not just like a coffee filter, in order to, you can get rid of any excess and do some very quantitative stoichiometric calculations with the precipitate that you produce. Titration is a technique that we use to determine the concentration of an unknown solution. So what you have is a burette which contains the titrant. Okay, the titrant is the known concentration. Okay, and we have these little volumetric measurements so that we can know exactly how many milliliters of it or what volume of it we're adding. In the bottom, in the flask, you have your analyte, and this would be your unknown. So you may not know the concentration of this analyte, but you know how many milliliters of it you have in the flask, right? So what you do is you add a known amount of this titrant and react it with this analyte in a definite known proportion. You stop the addition of this titrant when the equivalence point is reached. And the equivalence point is when the moles of the analyte are equal to the moles of the titrant. Okay, that's when you stop. The fixed volume of the analyte is measured using a pipette into the flask. So we measure along the burette here, the known volume. The titrant is added very slowly. We use indicators, colored indicator drops to the flask that will indicate when the end point of the titration is, so that we know when the analyte is completely reacted with the titrant, or that point at which the moles of analyte equals the moles of the titrant. The volume of the titrant then required can be directly read from the burette and used to tell us what the concentration of this analyte is. Here are the basic laboratory steps for titration. Should you want to see more examples on titration or calculations on titration, you can see Module 6 of this course. Part 3 is all about titrations of acids and bases and buffers. So to set up a titration, first the burette is rinsed with the titrant and then filled with it. Remove any air bubbles from the stop valve by draining a few drops so that the tip of the burette is also filled with the titrant. The pipette then is rinsed with the analyte. Then pipette the analyte and transfer it into the flask. In acid-base titrations, a few drops of indicator, usually an organic acid like phenolphthalein or bromethymol blue, that can change color in acid-base medium will be used. The indicator will be added to the analyte in the flask prior to the titration. The end point is reached when the first permanent color change takes place. At that point, the moles of the titrant are equal to the moles of the analyte in the flask, and we can use the equation M1V1, where M is molarity and V is volume, equals M2V2 to determine the unknown concentration of the analyte or titrant. In a titration, you're finding the unknown concentration of an analyte. Sometimes in a calculation problem, you would find the titrant. Let's now discuss reading a meniscus. The surface tension of a liquid can cause the liquid to curve up, like you see here, which we call convex, or curve downward, which you see here, which we would call concave. Either way, when you read the meniscus, in other words, when you're reading the volume of the liquid, make sure you read from the center of the liquid, either the top of the upward bulge, so right here, or the bottom of the downward bulge, so from right here. That way you get an accurate volumetric measurement every time.